All right, guys, today we got the multiplication rule with complements and conditional probability. And it's going to be the word and again, but, some special cases. So let's see what they look like. The first one is probability of getting at least one of some event. And basically what this says is find the event that among several trials we get at least one of some specified event. So when you see the words at least one, that's kind of what half of today is about. The second half is conditional probability. And conditional is just finding a probability of an event occurring when you have additional information that some other event has already occurred. So what are the chances of something happening after a different event has already occurred? Because sometimes a previous event will change the probability of something that's about to happen. Complements. This is the first half of today. Complements, it's usually best to solve at least one problems backwards. The complement of at least one, remember complement means the probability that it does not happen. So the probability of at least one not happening is no occurrence of it. So what we're going to do is we're going to solve for no occurrence and then subtract it from one, which you'll see on the next slide. An example. Not getting at least one defective DVD in a lot of 50 DVDs is the same as getting no defective DVDs. So they're going to be asking you today a lot of what's probably getting at least one of these, and what we're going to do is we're going to kind of go backwards and solve it with the complement. The steps are right here. Defining the probability of at least one of some event, we're going to roll like this. We're going to say probability of A is getting at least one. So that means the complement is getting none, because that is the opposite of getting at least one, is getting none. Then we're going to find the probability of the complement, the probability that you get none or the A does not occur. And then we're going to subtract it from one. Written everyday language, it looks like this. The probability of at least one occurrence of event A is 1 minus the probability of no occurrences of event A. Let's look at an example. All right. Telfer Development supplies X data DVDs in lots of 50, and they have a reported defect rate of 0.5%. So the probability of an individual disk being defective is 0.005. It follows that the probability of a disk being good is 0.995. In other words, a complement. If a quality control engineer wants to carefully analyze a defective disk, what is the probability of her getting at least one defective disk in a lot of 50? Is the probability high enough that the engineer can be reasonably sure of getting a defective disk that can be used for her analysis? So in order to find out the probability of her getting one, knowing the fact that she's getting 50 of them, first of all, the probability of A, let's go to this, probability of A would be 0.005. The complement of A, which is defective disk, a disk being good would be 0.995. So what I'm going to solve this is I'm going to solve for this one. What's the probability of getting 50 or finding a complement? So then all 50 disks are good. So instead of taking each individual one and doing the probability that it is bad, I'm going to do all 50 that are good. So the probability that all 50 are good would be 0.995 times 0.995 times 0.995. I would have to do that 50 times, because those are the multiplication symbols. And I would just keep on going. The quicker way, obviously, is to take your calculator and just punch in 0.995 to the 50th power. And when I do that, I get 0.778. So that right there, that probability right there is the probability that out of the 50 she chose, she has that much chance of them all being good. So that's not what we want to know. Though we want to know what's the chances that she gets at least one bad one. So I'm going to subtract that from 1. 1 minus 0.778, and I would get 0.222. That is the probability of her getting at least one defective one in that lot of 50. Now the question also asks, is the probability high enough that the engineer can be reasonably sure of getting a defective disk that can be used for analysis? And the answer is no. The probability is not very high, so she should probably start with more than 50 if she wants to make sure she gets at least one. So she only has, percentage-wise, you'd say she has a 22% chance of finding one, which isn't very high. Probability 0.222. Hope that made sense to you. That's what, half of your homework is going to be that tomorrow, is just solving at least one problem by doing the complement of at least one, which is none. All right, the second half of today is about conditional probability. The definition's on the top of the screen there. A conditional probability of an event is obtained with the additional information that some other event has already occurred. It's symbolized this way: probability of B given A. We saw that same notation yesterday. It denotes the conditional probability of event B occurring given that A has already occurred. It can be found doing this formula right here: A and B, which is basically multiplying them together, or finding the probability of A and B both occurring at the same time, over the probability of just A occurring, which is the first one. Quick example down here on the bottom. Not going to work it out, but just to show you what conditional probability means. It says the probability of a golfer making a hole-in-one is 1 in 12,000. And of course, that's based on past results. You really can't work that out mathematically. But if you have the additional knowledge that the selected golfer is a touring pro, the probability changes to 1 in 2375, which is a lot better. In general, a conditional probability of an event is used when the probability is calculated with the knowledge that some other event has occurred. So the knowledge of the fact that we had a professional golfer instead of just a regular golfer really changed that probability. And that's what's going to happen here. Okay, so an example here. It's the same one we've looked at all chapter. You should be familiar with this table by now. It says if one of the 1,000 test subjects is randomly selected, find the probability that the subject has a positive test result given that the subject actually uses drugs. That is, written this way: find the probability of getting a positive test result given that the subject uses drugs. So 2 ways to do this. One is the mathematical way, which is on the last slide. You can do this. You can do, first of all, do the positive test result and the subject uses drug. Those people right there are people who are both positive and use drugs. And on the bottom, just take the second part, subject uses drugs, that's this whole line right here, which is 50 over the 1,000. Now what happens here is your thousands cancel and you get 44 out of 50, which is about 0.88 probability. Now the other ways to do it this way, it's called the intuitive way, and to be honest, that's the way I usually do it the most. Is just intuition just means do what you know. So it says find the probability of the positive test results given the subject uses drugs. So when it says given the subject uses drugs, all I'm looking at is that. That's all I'm looking at. So if that's all I'm looking at, what is the probability that I get a positive test result? Well, there's 44 people with a positive. There's 50 people in that row. It's 44 out of 50, which is the exact same thing I got just a second ago. So that's called the intuitive way. You can go either way. You can do the math method, or you can be very intuitive and do it that way. Let me show you one more here in part B. Part B says if one of the 1,000 test subjects is randomly selected, find the probability that the subject actually uses drugs given that he or she had a positive test result. Written out like this: probability uses drugs given that positive test result. So I'm going to go backwards this time. Let's go intuitive. Intuitive part means I'm just going to look at the second part, given positive test results. So all I'm looking at is this right here, just those people. All right, because those are the only people who had the positive test results, and I know that's all I'm looking at because that's what I'm given. It says, what's the probability that subject uses drugs out of that? Well, it was 44 people used drugs. There's 134 in that column altogether. And if you punch that in your calculator, you get like 0.328 probability. Now, if you like the math method better, you would say, well, you would do both of them. How many subjects used drugs and had a positive test results? Well, there were 44 that did that. So 44 out of 1,000. Then you do just this part. How many people had a positive test result? Well, 134 did out of 1,000. And the thousands would cancel. You'll get 44 over 134 again. So obviously you get the exact same answer. So either way is fine. Just be very careful that you do realize that there's a condition there. All right. Warning, watch out for false inverses. In general, matter of fact, almost all the time, this is hardly ever true. The probability of B given A does not hardly, it should be a not equal sign in there. Never, hardly ever equals probability of A given B. The last slide, the last example, I can't go back here on this video, I wish I could, but the last slide was a great example of that. They did it both ways, like they did given a subject uses drug, has a positive test result given that they use drugs, and they also had probability of positive test result, subject using drugs. So they turned it around in the last problem. You can go back and look at that, and the probabilities were really different. Okay, here's an example, maybe to make it more clear, and this is it. We'll be done after I read this to you. Consider the probability that it's dark outdoors, given that it's midnight. Okay, so here's our probability right here. Probability that it's dark, given that it's midnight. That equals 1. We conveniently ignore the Alaskan winter, blah, blah, blah. But the probability that it's midnight, given that it's dark, is almost 0, because the probability of dark, given it's midnight, is 1, but probability is midnight just because it's dark is almost 0. We can clearly see in this case that the inverses are not true. Confusion of the inverse occurs when we incorrectly switch those values or think they're equal. They're hardly ever equal. I hope I didn't screw that up too bad. It made some sense to you. The probability is dark given it's midnight is 1 because it's midnight and it's dark. Okay. However, you can't go the other way. You can't say the probability is midnight because it's dark. Just because it's dark, you can't say, oh, it's midnight, it's 1. The probability is 1. No, it could be a lot of different times. So, two completely different things. Hope that makes sense. You can't turn them around. And we'll work on this like we always do tomorrow. And I look forward to seeing you then. See you. Bye.